High up in the mountains, every curve tells a story of balance between nature and engineering. When the slope is too steep for a straight road and cutting deeper would mean fighting the mountain itself, we bend. Not just any bend, but a hairpin bend, one of the most elegant yet challenging designs in highway geometry. These curves aren't drawn by guesswork. Behind every turn lies a precise philosophy defined by radius, superelevation, side distance, and the physics of motion. Each one must allow vehicles to climb safely, turn smoothly, and stay within the limits of comfort and control. In this video, we will explore how engineers think, calculate, and draw these iconic turns, from the geometric criteria to the design logic that brings them to life. Let's begin with the fundamental philosophy and criteria that governs the design of hairpin bends. For this video, we'll focus on the standard bends, both symmetric and unsymmetric. The skewed bends, that's a story for other day, which might be available shortly on your demand. Let's start right from the alignment plotting. Back in the theodolite era, intersection points and deflection angles were all computed manually out there on the field. But today, with modern survey tools and softwares, these calculations happen digitally, giving us far greater precision and flexibility. Once you have surveyed your corridor and plotted the IPs, you will often notice, especially in hilly terrain, some turns look too sharp for comfort. If your measured alignment deflection exceeds about 120 or 130 degrees, that's your cue. It's time to design a hairpin bend. For a basic hairpin bend, start with a circle with center at IP and radius RM, that's the radius for the main curve. From the intersection, measure a distance x along one arm and draw a tangent to main circle from that point. Repeat the same for the other arm. If the terrain demands an unsymmetric leg, feel free to use different values of x for each leg. At the newly formed junction, draw another arc with radius RA, the radius of approach. In this video, we will treat the upper curve as the approach curve, the central one as the main curve, and the lower one as the exit curve. You can set the exit curve's radius equal to or different from the approach. It's up to the designer's judgment. And that's your basic hairpin bend layout. Simple, geometric, and fully customizable. Now let's dig into the theory behind this geometry. Here's our diagram with all the geometric lines drawn and key points labeled. In this diagram, the known variables are alpha, the interior angle of the alignment, which equals 180 degrees minus the deflection angle. Rm, radius of main curve, which is selected based on terrain and road class guided by regional standards, which generally limits it to a minimum of 15 meters. Ra, radius of approach, which is at the designer's discretion. The unknowns are beta, x or OD, and gamma, the actual deflection angle of the main curve. Let's begin without transition curves. By basic geometry, the tangent length of the approach curve is given by CD equals RA times tan half beta. For triangle OBD, using the tangent relation, tan beta equals RM by BD, where BD equals BC plus CD. After simplification, we arrive at a quadratic in tan beta by 2. Solving it gives us beta. But notice one extra variable, BC, the straight portion between approach and main curve. This length is a design choice, but for simple hairpin bends, BC should be greater than the transition length specified by your national guidelines. Once beta is known, x can be directly computed as x equals Rm by sin beta. And that fulfills all the requirement for our simple bend. But simple bends are not so smooth. So for the smoother glide over the curve, we introduce transition curves, which changes the geometry slightly. The approach curve extends to include the transition, and a new point E between B and C is introduced. The length AE now becomes the tangent length of the main curve with transitions included. Now that our geometry is updated, the tangent length CD is calculated using modified equations for the combined curve, where the variables are as given. and same is for the AE. Using basic geometric relations, we can derive BD, AB and gamma as well, which are as follows. CE can be expressed as BC minus BE, which we can break down further. All the variables are now known. Plug them in, simplify, and you will get the working equations. The CE value represents the straight portion between the approach and main curve. For design with transitions, CE can even be 0 since the transitions themselves provide the necessary smoothness, but it is up to the designer. Now solving this analytically for beta isn't practical. It's messy and time consuming. It can be calculated by scientific calculators directly. Instead, we'll use the shooting method, an iterative approach. Let's take a quick example. With general variable values as follows, the shifts for both curves can be computed. And gamma is given by gamma equals 180 degrees plus 2 beta minus alpha. We will assume two starting beta values, say 30 degrees and 35 degrees. Assuming them slightly more than the value of alpha helps a lot. Now that gives gamma as 212 degrees and 222 degrees respectively. Next, calculate CE for both cases and interpolate for the target CE value. For our calculations, CE equals 0. Which yields beta equals 38.2 degrees. After one or two quick iterations, we land at beta equals 38.805 degrees, which we can now use to compute x. The same process applies to the other leg. And again, each side can have its own independent parameter depending on the topography. And that wraps up the theory behind the normal hairpin man. If you would like to see how skewed or irregular hairpin geometries are handled, let me know in the comments. Meanwhile, the civil 3D design walkthrough for this very hairpin bend will be uploaded next week, so stay tuned.